Hey guys, Professor Goodman. Welcome to part 2 of the video going over our final exam review. So the non-credit test review in eMath is the one that I'm working on. So here's what we're going to do in part 2. We're going to do our p-values. So we're going to do talk about p-values and so on. Remember, a p-value is just it's the probability of your test statistic in the direction of your tailed test. So if you're doing a left-tailed test and your test statistic is negative 2.3, the p-value would be the area to the left of negative 2.3, right? So then we're talking about hypothesis testing. So we'll go over a few hypothesis tests, and then the difference between z and a t-test. I think we start with z-tests and hypothesis testing, and then I talk about t-tests. Then difference in population proportions, then confidence intervals for two population proportions, and then the difference in two and independent samples. I'm only going to do one problem from this one because you guys just did the homework for this, right? It was for the basically hypothesis testing with two means with independent samples, right? So you guys should have that you should have that down now after you're probably now still doing the homework for it. Because it isn't due until Monday, so you guys probably are still doing that. If you are not, then you should have already finished it, right? Okay, so let's do this. So let's go to starting with problem 66, or actually 65. Okay, so here we have two hypotheses. So proportion of U.S. citizens who attend college immediately after graduating high school is 62.5%. The proportion of U.S. So that's my null hypothesis. My alternative hypothesis is the proportion of U.S. citizens who attend college immediately after graduating high school is less than 62.5%. So a left-tailed test, right? So let's say we took some kind of a survey and they found the p-value was 0.067. So remember, your procedure for if you reject the null hypothesis or you fail to reject it depends entirely on your p-value and alpha. So if your p-value is less than or equal to alpha, you reject the null hypothesis. You reject h sub 0. If your p-value is greater than alpha, you fail to reject. Emphasis on the fail. You don't accept the ho because it's technically not true. So do not accept your null hypothesis. You fail to reject it. Alright? So that's my p-value, right, is less than or equal to alpha, reject null hypothesis. P-value is greater than alpha, fail to reject null hypothesis. Okay? So let's see this. So this p-value is 0.067. So it is greater than my alpha, which I think they give you your alpha somewhere. If it doesn't give it to you, I guess assume it's 0.05. But anyway, even if it's 0.05 or 0.01, those are the kind of the two main alphas we get. You would reject it at any level. So you would fail to reject it at any level because the p-value is greater than alpha. Okay, so since the p-value is going to be greater than your alpha, that means that whatever data you found was not significant enough to reject the null hypothesis. So you failed to reject it because you couldn't find significant evidence. So the data does not provide significant evidence to conclude that that at least 62%. What? Not at least. It's less than, right? Because at least is not the statement we are trying to show. We are trying to show less than 62.5%. So we would say the data does not provide significant evidence that less than 62.5% of the U.S. citizens attend college after graduating high school. So this would be the answer, right? So make sure because it says do not provide significant evidence, right? So that's right, but so is this one. A lot of them say it. So make sure that you are getting the right second part of the question too. Make sure you're putting in the correct claim. The correct claim is your claim, which is less than this. Okay? Good. So now 66. So in 2012, Americans Veterinarian Medical Association released a report that 36.3%. Oh, who cares? Something about cats. Here is what actually was found. Suppose that the following conclusion was made. The data observed does not does not provide significant evidence that more than 36.3% of U.S. households own at least one cat. This means that the p-value was too large, so it was larger than my alpha level of 5%. Right? If your p-value is too large, you did not find significant evidence. If your p-value is small enough, you did find significant evidence. Right? So since my p-value is some value that has to be greater than this one, select all the values that are greater than 5%. So this is not even a full percent. So this guy's less than it. This guy's 40%. This guy's 17%. And this one is negative 1.07%. That's not even a p-value. So that's not cool. So that's definitely not even an answer. I don't even know why it's there. That's maybe because it's trying to screw you up in case you're calculating your test statistic. So there you go. So just go with the ones that are greater than 5%. So now look, same kind of problem, but look. Now it says, the following conclusion was made. The data observed provides significant evidence that the average difference in GPA between male and female students is less than 0.1 points. Which of the following p-values support this conclusion? So now we had data that was significant, right? So this means that we look for the p-values that are less than 5%. This is 19%, so no. 31%, so no. This is 9%, so no. This is 0.49, right? So this means that it is, or 0.049. This means that it is 4.9%. That is less than 5%. And this isn't even a full percent, right? It's a tenth of a percent. And there you go. So that's all you had to do for that. Okay, now 71. So problem 71. Gallup poll published that 28% of Americans feel the national defense and military spending is too low. Which of the following samples meet the minimum sample size criteria for a z-test against the null hypothesis? P is equal to 0.28. So this is testing this. Remember, for your proportions, you would hope, which it always is, so you just have to do it for these few problems, but you hope that your n times p is at least 10, and then you hope that your n times 1 minus p is at least 10. Okay, so we just got to check these. So multiply your n times p, or I mean, I guess in this case, we're trying to find the n, right? So what I would do is, it's the same as n is at least, just divide both sides by your p, right? It's simple math here. So if you divide both sides by p, then it's n is at least some number. Divide both sides by n 1 minus p, then n is at least some number, 10 divided by 1 minus p. So go ahead and do these guys. Okay, so what are these? Well, p is 0.28, right? So if my p is 0.28, should have put that kind of on the top. So if my p is equal to 0.28, then this would be 10 divided by 0.28. So it would be 10 divided by this. Okay, so 35. Then this guy. 10 divided by 1 minus p. Okay, it's as simple as that. So this is round up to the nearest whole person, because if we're talking about a sample size, they have to be a whole sample, right? You can't have 35.71 of people, right? You can't have a 3/4 of a person almost. You have to have a whole person, so it's the next whole number up. So 36 and then 14. So now the 14 is smaller than the 36, right? But 14 satisfies this condition, right? So that's okay. But the problem is the n you choose has to satisfy both conditions. So you have to go with the larger n, because the 36 is going to satisfy this condition. The 14 will not satisfy this condition, right? But the 36 will satisfy this condition and this one, because 36 is larger than 14. So 36 is the minimum size. So n would have to be at least 36. So all you have to do, look at these and choose all the ones that have n is at least 36. So 2,000, 2,500, 2,000 again. I guess, whatever. I guess there's two 2,000s. I don't know, maybe one of them's wrong. And then 48. So all the values that are more than 36. Okay, so let's see. Okay, and there you go. And that's all it is for that one. Not too hard, right? Okay, so now we'll do some hypothesis testing. So that has to deal with p-values and your sample size n and so on. But here we go, is an actual hypothesis test. All right, so in a recent Gallup poll, oh gosh, the Affordable Care Act again. Here we go. 61% of Americans support the replacement of the Affordable Care Act with a federally funded health care program that provides insurance for all Americans. Congressmen from a certain state, okay, that's the hint, a certain state, believe this poll is not representative of their constituents, and the state percentage is lower than the national percentage. So they conduct a statewide poll. So look now, a statewide poll. So a random sample of 2,500 responses are chosen. These are 2,500 people from that state, showing that 1,025 of the state citizens support the replacement of the ACA. So here, what group are we making a hypothesis for? So what's our HA in this case, or our alternative hypothesis? Well, what are we dealing with? Well, here we're looking now at the state level. So we think, okay, we think on the federal level, or the all Americans, so on every state, we don't think that this congressman does not believe that it represents their home state, or their state. Well, they think that maybe there's a different something different with their state. So they conduct a statewide poll. So in other words, now my population is not all Americans, it's the state. So it'd be the population of state citizens. That would be your answer, right? So my population changes from all Americans to the state. Okay, so what is the proportion p0 for the null hypothesis, right? This just means what is my p equal in the null hypothesis? Well, remember, in your null hypothesis, it's always what is believed to be true. Well, here we're saying, it says that the state proportion is the same as the federal proportion, or the one that's already been given, so the 61%. So it'd be 0.61. Right, my 61%. So that would be my proportion p0 for the null hypothesis. So here, how do the congressmen think that the state citizens will compare to the 61% of U.S. citizens that support the replacement of the ACA? So here, this is just asking you, what is the claim? What is your alternative hypothesis talking about? Well, here they say they believe it's not representative, and they say that the percentage is actually lower than national percentage. So they think the state's proportion will be smaller than the national proportion. Okay? So now they want us to find our null and alternative hypotheses. Now remember, the null hypothesis is H sub 0, and it's always equals. So this is the correct null hypothesis because P is equal to 0.61, which 0.61 is my p0, right? So perfect. That's the null hypothesis. Now the alternative hypothesis. It's always some kind of a contradicting statement to my null hypothesis, but that it deals with the claim that I'm trying to show. Well, what am I trying to show? I'm trying to show the state's proportion is smaller than the national proportion, which means my p is actually smaller than 0.61, right? So then my HA, or my alternate hypothesis, would be p is less than 0.61. And there you go. Okay, so what does the proportion in the null hypothesis represent? So now it's saying, what's the proportion? Well, the null hypothesis was talking about the entire U.S. population. So it would be the proportion of U.S. citizens, so all U.S. citizens who support the replacement of the ACA. U.S. citizens who, geez, which one do we click? Oh, okay, not number. What is the proportion? The proportion says, oh geez, what the heck? I haven't seen this one before. It's the it wouldn't be the number, it's a proportion, but that seems kind of vague. Would this be correct? Oh, I see. Guess they're already saying the proportion, so they're not saying the proportion is the proportion of. It would just be the number of U.S. citizens, right? So it'd be the number of U.S. citizens, because the proportion is saying that your successes over, or the number of your successes over the total that you're studying. So it'd be all of the people. That's what the proportion is representing. So the number of U.S. citizens who support a replacement. So yeah, sorry, this one should be, what? It says the proportion in the null hypothesis. So, oh, okay. Sorry, I was reading that incorrectly. They're saying this is what the population proportion is representing, right? They're saying this value is the population proportion, but as soon as we start the hypothesis test, the null hypothesis is assuming that the proportion of state citizens who support the replacement of the ACA. So as soon as we start the hypothesis test, throw out the idea of the population proportion, because we're dealing now with not the population of U.S. citizens, we're talking about the population of the state citizens. So it should be, now is it number or is it state? Now I'll just look. Okay, yeah, proportion. So, sorry about that. I don't know. When I was thinking null hypothesis, I was thinking about what does the 61% actually represent? If they were asking me what the 61% represented in the beginning of the problem, it would have been the federal level. It would have been the entire U.S. population. But because it's saying the null hypothesis, as soon as we started this hypothesis test, we're dealing now on that state level. So it would be the proportion of state citizens who support the replacement. So sorry about that. Oh, sometimes, it's actually kind of good sometimes that I make these mistakes. That way you guys know what not to do on a test. Because I'm definitely not perfect. I make mistakes too. Okay, but here we go. So now here comes the, let's see, do they not tell us the p-value? Okay, we got to find our test statistic and p-value now. All right, so let's get all of our information and throw it on in, right? So here, I need my hypotheses. So here's my null hypothesis. We say p is equal to 0.61. Then my alternate hypothesis, I say p is actually less than 0.61. Oops, 61. So if it's less, this means it's a left-tailed test, right? So left tail test. Okay, now I have my p. I need my p hat. I need my n. And then that should help me find my standard deviation. Okay, and then once I find that, I can find my test statistic. Now remember, your test statistic for a proportion is always z. So it's always going to be your z, and then we'll find our p-value after that. Okay, so my p, now I'm trying to get p and p-value mixed up. P-value is the probability of your test statistic. P is the proportion beginning in the problem. So p, remember, we're assuming that the null hypothesis, we're assuming h sub 0 is true, so then my p is 0.61, right? So then because assuming h sub 0 is true. If h sub 0 is true, then p is 0.61. Now let's look at my p hat. So my p hat was the 2,500 people, that's n, so 2,500 people, and then how many people said yes? 1,025, so 1025. So p hat would be equal to the 1025 people divided by 2,500. Okay, so 0.41. Whoa, that's way smaller, but let's see if it's small enough to reject. All right. So standard deviation for a proportion, remember, it is the square root of your p, because you're assuming p is 0.61, so p times 1 minus p divided by square root of n. Oh, no, we're already square rooting, so divided by n. Okay, there we go. That's my standard deviation. All right, so my test statistic. Well, didn't really need to do that, I guess, but well, made it easier for us. But that's not how I was teaching it to you guys. So let me kill this part, and then we'll do it how I was normally teaching you guys. Okay, so my test statistic is my difference in my p hat, so p hat minus p, divided by the square root of my p times 1 minus p divided by n. Okay, so that's my test statistic, so negative 20.5. And now it's a left-tailed test, so my p-value is going to be, of course, it's norm.s.dist, because it's always, this test statistic is a z-score, so you can always use this. And it's to the left. And of course it's normal because we're dealing with proportions. All right, and there we go. And this just means it's 0, right? This is 1.02 with 92 zeros in front of it, and you move the decimal place that way 92 times. So definitely p-value of 0. So here, what conclusion can be drawn with the p-value or test statistic? Use significance level of 0.05. Well, the p-value is 0, which is definitely smaller than 5%. So we say, since it is extremely small, we can reject the null hypothesis and conclude, and then we conclude our claim, right? Our claim was, we think that less than 60% of the state citizens support the replacement. And there you go. That is how you do this part. Oh, and then it asks for the test statistic. That's weird. Okay, so my test statistic, so we already have that, thankfully, so throw it over here. And then 5 places after the decimal. So 1, 2, 3, 4, 5. So the 9 makes it a 1. And there we go. So pretty large test statistic. Okay. All right, now these two guys, these few guys are kind of weird, but I'll show you how to do them. The best way to do these are to eliminate things. So like do an elimination, because a lot of them, like, they don't actually give you like the procedure, because we're used to using the procedure, but in this case they don't. They just say, hey, here's a picture, figure out all the information from the picture. Okay, so first things first, what I would look at is identify which of the hypothesis tests are correct. All right, so remember, your null hypothesis, so the h sub 0, it's always equals. So right off the bat, kill this one, right? Because this one doesn't have equals. So this guy is not an answer, right? So one of the ones that has p equals is one of the correct answers. Now here comes the next part. So try to identify, now we're going to look to find out which ha is the correct one. Well, the p-value is area to the right, right? So to the right of our test statistic. So if it's to the right, it means that our ha, or our alternative hypothesis, has to have a right-tailed test. Well, which one of these has a right-tailed test? Not this one, so we kill this one and this one, so the first two are wrong. This one's a right-tailed test, and so is this one. So these are our two options right now, because this one down here is not even right. It's never going to be equals. So these two are our solutions. So now only thing that's different now is the z. So which of these z's is correct? Well, the z is talking about your test statistic. Well, what's our test statistic? It's positive 1. So then the negative 1, throw it away. This is my solution. And there you go. You did it right. So now do the same thing here. Well, now it's a left-tailed test, right? And my z is negative. So first things first, look for the left-tailed tests. So the ha has to be to the left, so it's either these two, but now it's a negative z-score, so it's this option. And ta-da, see, really fast. This one, there's a little more going on, but it's the same thing. It's a two-tailed test, so look only for two-tailed tests. This one is a two-tailed test, so is this. This one is not. So these last two are incorrect right away. Now we look at these two. So this one says the z is negative 1 or z is positive 1. Okay, so this one seems correct. Let's look at this next guy and see if there's something wrong. So this one says z is negative 1, which is correct, but oh, look at this. The second ha is incorrect. They say equals for 1. So this is definitely not the correct answer. It's this one. So be very careful when you're looking through those problems, because if it's a two-tailed test, your ha needs to be p is not equal to 0.35. Right away, this one's wrong because this says that your null hypothesis is p is equal to 0.41, but this one says that your alternative hypothesis is equals to 0.41. So there's no difference in like the null hypothesis and your alternative hypothesis. So this is definitely not a right answer. Okay. So there we go. So now let's go to, we're in the home stretch, just a few more problems. So problem 80. Oh, jeez, I'm so done with this. Oh, so many problems. I can't even imagine having to do every single one of these. But hopefully this video helps you guys out enough to where you'll feel prepared for the final. But here we go, our next one. So American Pet Products Association has been gathering statistics on pet ownership in the U.S. since 1988. The publish of the results of the National Pet... Their report said that an average of $1,436 per dog per year on veterinarian care. So veterinary care. So good job, vets. Take a lot of money per year per dog. The American Vet Medical Association, established in 1863, believes that the average amount of dog owners spend each year per dog less than this. So they think, hey, actually, we're better than that. People don't spend that much money. So then they publish the results in this pet ownership book every 5 years. The 2012 stated that the dog owners spend an average of only $227. So that's a big difference, right? Or that's each year, I see. Oh. So this is, says that spend each year per dog is less than this. And then they said their 2012 report stated that dog owners spend an average of $227. Okay. So I don't know why, but the numbers just seem way too big for me. Like I said, it just seems crazy. So let's see if I'm missing something. On average, per dog per year, the average amount of dog owners spend each year per dog is less than this. They publish results every 5 years. And then, so does that mean I multiply this guy by 5? Let me look. Like what? I'm not exactly sure I understand this question. Test statistic. So do they multiply their x bar by 5, or do they just use 227? Because that number just seems so much smaller to me. So I don't even know why someone would say $1,436. I don't know. Maybe wherever these people looked before. So the pet owners survey, national pet owners, wherever these guys looked, they must have looked in a place where like their dogs are made of gold or something, because that's a lot of money. And then it's like, actually, look at this, only $227. So sorry about that. I was kind of psyching myself out. Let's just get to the problem. So in the APPA survey, represents the population, and the A represents the sample. What are the null and alternative hypotheses? Okay, so remember, your null and alternative hypothesis deal with your population data. So the H sub, the H sub 0, or the null hypothesis, will say that it's equal to what is believed to be true, which is the 1436. So the H sub 0 is equals 1436. Then the null hypothesis is, the alternative hypothesis goes with our claim, which our claim, they say actually they spend less than that amount. So it'd be the same numbers, but ha, and then mu is less than that amount. So this would be my two hypotheses. Okay? So now we're going to find the test statistic. They give us our population standard deviation, so let's go back to this. So now it's a mean problem. So mu is equal to something. It should be 1436. And then we say mu is less than 1436. A lot of left-tailed tests. Okay, this is my mean. So mu. Now this is my x bar. So my sample mean, my n, and then my test statistic. Can't do these guys right away. We have one more bit of information we need, which is the standard deviation. Okay. So my mu, first off, is 1436. We assume that the hoe is true. Then my x bar was my sample mean, which was the ridiculous 227. So that's super small. So it's going to be a humongous test statistic. And how many did they say that they looked at? So, holy wowza. Did they look at 88,000? Oh my gosh, that's a huge, well, yeah, I guess so. Okay, well, 88,000 people. I'm surprised that wasn't the population, because that's just vets. Yeah, so veterinarians, I guess. So I guess that would make sense. Okay, so then my standard deviation, they give me the population standard deviation, which is the 557. So 557, so a little bit of spread there. Okay, so now we find my test statistic. Now, does the central limit theorem apply? Well, is this guy greater than 30? Yeah, definitely. So we have and our population standard deviation is known, so it is definitely a z-test. Okay, so let's find our test statistic z. So what we do is we take my x bar minus mu divided by my, open parentheses, standard deviation divided by the square root of n. And there you go. So my test statistic is a very large 643. Okay, so now look at my p-value. So p-value is is the probability around your test statistic in the direction of your tail. So it's norm.s.dist because it's a normal distribution. This z, comma, always cumulative. So 0%. So very small. So what is the test statistic? Well, it's this horrible thing, a humongous thing. To 5 places. 1, 2, 3, 4, 5. So this will be 3. Okay. So there we go. Now, the variance between the population is quite unusual. Both the okay. The APA's calculation AMV includes routine vet visits without surgical procedures. Mu naught is this, and standard deviation is this. What does the new test statistic for the population mean? What? Okay, so they're changing the problem slightly. So now mu naught, this means the alternative hypothesis and the the null hypothesis and alternative hypothesis, the number is going to change to 228.25. So this is, okay, let me in there. So 228.25. I think that was the number, right? 228? 228.25, good. Okay, so 228.25. Okay, so these are my two hypotheses now. So 228.25. And check this out. So I just do this and voila! It changes. So, and then of course my standard deviation changes to 95. So 95. I think they said the same amount of people. Yeah, the sample size doesn't change. Okay, so look, because I changed my mu and I changed my standard deviation, but I was calling up everything, it's all still the same, right? I don't have to change any of this other stuff, and I get these nice values. So let's see. Man, that's it's still pretty small, but let's see. So this is my test statistic now. So try to do that when you guys are doing your tests. Try to leave values in Excel where you used the actual cells from Excel, earlier. So that way you don't have to type out all these formulas or functions over and over again. Okay, so we went to 5. So 1, 2, 3, 4, 5. Okay, so the 6. Okay, and we got it. Very nice. Okay, so that was problem 80. So let's go to 81. So first things first. We're given our life expectancy, 78.7 years. They say the life expectancy variable varies normally, but the population standard deviation is unknown. Uh-oh. We have to use a t-test, right? Because as soon as the population standard deviation is unknown, you go t, right? So if pop standard deviation known, this means you have normal, right? Or z-test. If population standard deviation unknown, it's t-test. So these are two things you have to do. So let's do this. Okay, so now all this stuff needs to change because now it is t, and then it's not standard deviation anymore. It's sample standard deviation. Okay, so all these guys will change. Okay, and so will these because we don't know if it's going to be a left-tailed or a right-tailed test. All we know is the null hypothesis is going to be equals, but let's check this out. Okay, so let's look at the problem. So the life expectancy of the average American is 78.7 years. So that's what we assume is true, 78.7 already. A researcher wants to know whether the life expectancy has changed. So be very careful. This doesn't mean necessarily it's a positive or negative change. It just means it's a change. So that means that it's either greater than 78.7 or smaller than 78.7, i.e., it's not equal, right? So 78.7. So there we go. So we assume this is 78.7. Okay. And then here we have some data. So we have 5 American males and 5 American females. So here is the data that we're going to use. So let's just throw it over here. Okay, so this is all of my data. So when I'm going to get my x bar, it's going to be the mean over there. So if I want x bar, it's simply the average of all of the ages, right? These are all how long people lived. So there's my average. Now my n, well, how many people were there? You can highlight all of the ages, or you can just remember that it was 5 females, 5 males, so it'd be 10. But down here it says that there are 10 people, so the count. So 10. So now I need my sample standard deviation. So your, but actually in this case it's kind of your standard error or whatever is what you're going to need to find for your test statistic. But my standard deviation is STD, and then it's .s because it's for the sample, right? So select all these guys. And where's I found an error? What? S? Did I accidentally? What did I do? H2 to Q2, HQ to Q2. That's fine. Yeah, I guess I must have accidentally put an extra set of parentheses or something. Okay, so that's my sample standard deviation. And now look, I don't have to actually change anything because I was using everything in Excel. But I will show you guys just because it's helpful for you to see. So the formula is the same. It's going to be your x bar, so equals, because you open yourself to the math world, your x bar minus mu divided by your standard deviation here divided by the square root of n. Okay? And then your p-value. P-value is t.dist, right? Because it's a t distribution, so you cannot, if you use norm for a t distribution, it is going to be off by even slightly, but it will be incorrect. T distribution, here's this, so my t score, and then my degrees of freedom is my n minus 1, and it's always cumulative. Okay? Now be careful here. So what kind of a tail test is this? It's a two-tailed test. So this is a negative test statistic. So which tail am I closer to? Am I closer to the left tail or right tail? Well, negative values means you're closer to the left tail. So I find the area to the left, which is what I did. But because it is a two-tailed test, find area of test stat in direction of closest tail, then multiply by 2. Because remember, in a two-tailed test, you have 2 rejection regions. To make up for the 2 rejection regions, you have to multiply your p-value by 2 to compare it to your alpha. So then click on this guy and multiply him by 2. 2 times my t.dist. And there you go, 32%. Either way, we were going to reject, fail to reject anyway. Okay, so now we have all the information here, right? So let's finish up this problem. So first things first, it asks for the null and alternative hypotheses. Well, it's a t-test, but that does not mean that our measure of center is t. We're still using means. So right here, the null hypothesis will be equal to 78.7. So mu is equal to 78.7. That's the null hypothesis. Now the alternative hypothesis, they want to know if it changed, which means for the its mu is not equal to 78.7. And there we go. So now what form of hypothesis testing would best fit this scenario? We already figured this out. It's a t-test. And why is that? Because the population standard deviation is unknown, but we still have some approximate normality. So a t-test would be the best form of hypothesis testing because the life expectancy variable varies normally and the population standard deviation is unknown. And there we go. That should be the correct answer. Calculate the test statistic for this hypothesis test. That's this dude. Okay, so copy this dude over, throw him in here, in 5 places. So 1, 2, 3, 4, 5. So this will be 1 and kill the rest. Okay, what is the p-value for the scenario? This guy. Okay, so 4 places. 1, 2, 3, 4. So this will be 6. So kill everything after 6. And there you go. So now what conclusions can be drawn? Well, the p-value is larger than alpha, right? Alpha is either 0.05 or 0.01. I think in this one it's 0.05. Doesn't tell us. Oh, here we go. Assume sigma is level 5%. So we have 32%, which is much larger than 5%, right? So then we would fail to reject. So since the p-value is greater than 0.05, we fail to reject, so not this guy. Since the p-value is greater than 0.05, we I don't like the accept, but I don't know. I've heard from some of my students that they say that that's correct, but let's see. Since the p-value is greater than 0.05, our results are not statistically significant, and we cannot reject. That's correct. Since the p-value is less than 0.05, nope. I want to say that's the only one. I don't like the whole accepting. Yeah. So it's definitely not accept. That is incorrect. Someone told me that that was one of the correct answers, and if it is, then that is an error, because in a hypothesis test, you never accept your null hypothesis. You can only reject it or fail to reject, because if you assume something is true, there's no way you can prove it's true, because you're assuming it's true. If you assume that it's false, you can try to figure out a way to prove that it is actually true, but in a hypothesis test, if you assume something is true, you are not proving that it is true at the end. You're only saying, oh, we found an example of it working out, but that is not a proof. That is an example. So you can never accept the null hypothesis. You only fail to reject it or reject it. So this would be your answer. Okay, so let's go to difference in population proportions. So it's 86. Yep. So, any NFL fans who attend NFL games on Sunday more likely to drive under the influence of alcohol than NFL fans who tailgate NFL games on Sundays? What an interesting question. Very nice study. A research team randomly sampled 30 games at various locations throughout the NFL season, including the playoffs. At each game, approximately 100 people who claimed to only tailgate the game were given a breathalyzer test prior to leaving. Okay, so 100 people who left the stadium at various times claimed to be driving when they were given this test. 1,200 who left the stadiums had a blood content above this, and 12,000 who tailgated had a blood above the state limit prior to leaving. Okay. So a research team randomly sampled 30 games. Okay, so sample size is 30. At each game, approximately 100 people were tested, given it prior to leaving, and approximately 100 people who left each stadium at various times and claimed to be driving were given a breath as their test. Okay, so never mind. It's 100 for each. Wait, what the? So 1,269 who left the stadiums had a blood alcohol content above the state limit. Okay, and 1,218 who tailgated. Oh, it's one of these problems. So it should be, they sampled 30 games. They approximately sampled 100 people who only tailgate, and then 100 people who left the stadium. So 100 at each one of these games. So at all of the games, they sampled 100 people, right? So that means that it's 3,000 total, right? I think that's what it's saying. So let's see. So let's see if my N is 3,000. So let's see. I'm pretty sure that's what it is. So it's one of these annoying problems. N1, N2, they don't tell you that it's 3. Of course they don't. All right, well, we'll just have to do it both ways, and then that way at least you guys can see if it's right or wrong. So you can copy what I'm doing, and hopefully it's right, but, you know, don't hit check answer until I've finished checking it myself, so you guys don't have to go through it all over again. Okay, so what I'm saying here, it's going to be a difference in proportion, so these are going to be difference in proportion problems. So let's kill all this. So kill all this stuff. Kill all these guys because everything's going to be different now because it is a two population problem. So let's get all of our data together. Well, first off, what's the null hypothesis? Well, the null hypothesis, it's always that the difference is the same, right? So that means that the difference is 0. So this just means that P1 minus P2, they're equal. So that's my null hypothesis. My alternative hypothesis then goes with my claim. They say, are NFL fans who attend games on Sunday more likely to drive under the influence of alcohol than NFL fans who only tailgate on Sundays? So in other words, is the proportion of people driving under the influence, is it greater? So is my first one greater than my second one, right? So my then would be P1 minus P2 is greater than 0. Because I'm saying my P1 is greater than P2. Because P1 would be people who attend NFL games, and then P2 is tailgaters, right? And we're trying to see if the people who actually attend the games, are they more likely to drive under the influence of alcohol than people who tailgate? Okay, so here are my hypotheses. So my H sub 0 is my P1 minus P2 is always equals 0. And then my alternate hypothesis is P1 minus P2 is greater than 0. So it's a right-tailed test. Okay, so keep going on. So we have to, first off, remember our P1 minus P2, because we're assuming that the null hypothesis is true, it's always 0, right? Because you assume is true. Okay, but now we need to find my P hat 1, my P hat 2. No, actually I'll find those in a second. I need my X1, so my number of successes, my X2, number of successes there too. And then I need my N1, N2. And then I can find my P hat 1, P hat 2. And what else do I need for the formula? P bar. Yes, P bar. Very important for a difference in population proportions. Okay, so let's look back at this problem. So first things first, we have 30 games, and at each game 100 students, 100 people are sampled for both. So this means your sample size N is going to be 30 times 100. So for the 30 games, so per game, we sample 100 people, and there are 30 games, so it's going to be 100 times your 30. So there's 3,000 for both. Okay. So now I need how many people had a blood alcohol content above state limit. So people who left stadiums, 1269. So that's my first one. So 1269. Because I'm just basically saying, let's just say in stadium, and then this was tailgaters. Okay. All right. So that's just what we're doing. So 1218. Okay. So this would be people in stadium. Sorry, and these would be the tailgaters. Okay. So here we go. So my p hat 1 would be the proportion of people who were above the state level in the stadium. Whew, that's a lot of people. 42%. Yikes. A lot of people above the blood alcohol content level. Well, I think they did at each game, 100 people were given the breath analyzer. That seems like a lot of people. Jeez. All right, well, it's a large p hat. Okay, so then now my x2 divided by n2 gives me my other one. So these are the proportion of people who were pretty much drunk, right? And then, or at least their alcohol content was above the state level. And then this was among the stadium, and then above the state level in among tailgaters. So my p-bar is my x1 plus x2 divided by x-men. No, I'm just kidding. Divided by n1. Ah! Stop! Okay, I know. I see it. Plus n2. Alright, so this is my p-bar. So remember, it's a value between these two guys. So if you get a p-bar that is not between or really, really close to these two guys, your p-bar is not correct. So that's a good way to make sure that you're going along this the right way. So now I can find my test statistic. So I have all this, I have this. Okay, what's the difference between my p hat 1, p hat 2? So you can find this too if you want to, I guess. I'll just do it down here. P hat 1 minus p hat 2. Because I don't do this until the actual test statistic, but whatever. So my p hat 1 minus p hat 2 is this value. So it just says throw it in as a decimal, so don't do any rounding. Okay, and hopefully we did that right. Yep, we did. Okay, so then multiplying it for the n is a good idea. The normal model is a good fit for the sampling distribution. Compute the pooled proportion and estimate the standard error. So this right here, we have to do our estimated standard error. So that just means your standard error. I hate that they split it up like this. Oops, error. Standard error is your, for a 2 proportion, your standard error is the square root of p bar times 1 minus p bar divided by n1 plus p bar times 1 minus p bar divided by n2. That is my standard error. Okay, so let's do that. So, square root. Okay, open parentheses for my p bar times 1 minus p bar divided by n1 plus p bar times 1 minus p bar divided by n2. Okay, so that's my standard error. Let's see, so round it 7 places. 1, 2, 3, 4, 5, 6, 7. This becomes an 8. And then the rest get killed. That's right, that's 7 places. Yes, 4 to the left, 3 to the right. Yay, green. Alright, so now we calculate the z-test statistic. So now that they made us calculate the standard error and everything, you know, you can do the shortcut because it's basically your z-score is equal to your difference in, test statistic. Your test stat z is simply put difference in p hats divided by your standard error. So standard error. Okay, so since we already have our standard error and we have our difference in p hat, you could just do it like that. So my test stat z is simply this guy divided by this guy. Or if you're someone who has the whole formula memorized, just go ahead and do it again. So test stat z, just go your p hat 1 minus p hat 2 divided by square root p bar times 1 minus p bar divided by n1 plus p bar times 1 minus p bar divided by n2. Okay, and see, we get the exact same thing. So you can do it either way. If you know to use that shortcut, you can do it, but in case you're like, I need to just do the whole thing over, go ahead and do it. It's fine. Okay, so we have that. All right, so we'll probably need our p-value too, but let's go back and look at the problem. They asked for a test statistic, so let's copy this over and throw it in here. Okay, so we need 5 places. So 1, 2, 3, 4, 5. So this becomes 0, this becomes a 1, and there we go, that's 5 places. Oops, dang it, what did I do? What did I, oh, did I not round it correctly? 1.36, what? 1.36, I put the right thing in there, right? Okay, maybe I just did a weird way of rounding. Oh, oops, I didn't change the 4, so it should be this 4. So it says 5 places, so it should be this. And that's what I did. I forgot to change the 4, so sorry about that. So there we go. So that is my test statistic. P-value now. Yep, need our p-value. So what am I going to do? Well, it's a norm because it's a proportion, so it's always norm. So z, and then it is 1. Now be careful, it is a right-tailed test, so we got to do 1 minus norm, right? Ooh, it's too big. So we got to make it a little larger. Dang, really wanted that much. Didn't need that much. Okay, so just remember when you see all those number signs, that just means that your cell isn't long enough. Okay, so then now it says round to 4 places. So let's copy this guy, throw him in here. It's 1, 2, 3, 4. So this is the 4th one, and everything else gets killed. Oh my gosh. What did I do? Did I do that again? Oh my goodness, really? I think I've been doing this stuff for too long. Let's just round it to 4 places. And then it shows me a lot more than 4 places. Okay, well, let me see here. So let's, oh, geez, what? Yeah, sorry, I'm really slow right now for some reason. Oh, back down to my 86, I think. It's 83. Oh, dang it. Gotta do that one too. But 86 was the one that I was working on. Should be this. Okay, cool. All right, so now last one. So interpret our p-value. Our p-value is about 9%. So it's larger than our significant level of 5%. So that means if it's greater, that means we fail to reject the null hypothesis, right? So this is no. The p-value means that there is no different. Oh wait, p-value is greater than the significance level. Therefore, we cannot reject the null hypothesis, and that there is. Oh my gosh, that there is no difference. That's definitely not correct. The p-value is greater than the significance level. Therefore, we accept the null hypothesis. That's not correct either. P-value means that if there's no difference in the population proportions p-value is greater than significant. Therefore, we cannot reject the null hypothesis that there is no difference. Okay, so they're just stating the null hypothesis. We cannot reject the null hypothesis that there is no difference between proportions who drive under the influence of alcohol and go to the game or not. All right, I think that should be the only answer. Oh, that's what it says. Okay, that's right. So, p-value means there's a 9.1 chance. It shouldn't be that one, right? Is it? Yeah, cannot reject the null hypothesis. P-value means there's no difference in population. Okay. Because this doesn't mean there's a 9.1% chance. It just means that p-value, there's no difference in population proportion. There's about 9.1% chance that random samples will have a difference less than this. So that's what your p-value means. Except that, oh, dang it, they'll have difference less than. It's more than, right? P-value, this one is good because we cannot reject null hypothesis, so there. The p-value means that there's no difference in the population proportions. There's about a 9% chance random samples will have a difference more than this. Okay, so remember, it's more than, not less than. I didn't read the last little bit. So make sure when you guys take the test, read all of it. Don't be lazy like me and not read all of it. Okay, so there we go. So now let's do a confidence interval problem. So let's head back to 83. So I'm backtracking to 83. This is for 2 population proportions. So 95% confidence level. So let's kill all this junk. And then we'll do this one. So we have 500 people are randomly chosen from U.S. population, 250 are randomly assigned to a treatment, and 250 are assigned to control groups. Okay, so I have my p-hat1, my p-hat2. I need my p-hat1 minus p-hat2. Then I need my n1 and my n2, my confidence level, which you can put there if you want to, and then my z. Okay, and then I need my margin of error m. So here we go. So my n's are 250 each, so 250 apiece. 250, 250. Oops, not 259. So 250, 250. My p-hat1, let's see, it says that 170 people in the treatment group had the desired effect. So my treatment group will be my n1, my control group will be my n2. 170 people divided by 250 is my p-hat1, so 170 divided by 250, or divided by my n1. Oh, I forgot to do equals. Just having one of those days. Okay, and then the other one was 50 people, so this is a pretty large difference. 50 divided by 250 for n2. And then the p-hat1 minus p-hat2 is this guy minus this dude. Cool, so there's a positive difference, so p-hat1 is definitely larger than p-hat2. So my z, they say use, is 1.96. My confidence level is 0.95, I believe, and 1.96. Okay, so then that's everything we need for a 95% confidence interval. So my margin of error, this is your z-score times the standard error for this problem. So your standard error for a difference in proportions is the square root of, so you don't have to put this here, sorry. So the square root of your p-hat1 times 1 minus p-hat1 divided by n1. That's the first one. Plus p-hat2 times 1 minus p-hat2 divided by your n2. Okay? And there you go. That's your margin of error. So now remember, we need our lower and our upper for these guys. So my upper is the difference in p-hat1 minus p-hat2 minus m. This is for the lower. So remember, it's just your p-hat1 minus p-hat2 minus m. So your measure of center, then minus m, and then this one is your measure of center plus m. So that would be the difference plus my m. And there you go. This is my lower and my upper. So let's see, what do I need them to be? I need them to be to 5 places. So let's do down to 5. I'm not taking this chance anymore. I've been rounding kind of badly, so I need to just let it do it for me. Okay, so both of them have been rounded to 5 places. So let's check our answer. And voila. Okay, so that is how you do the confidence interval. So, the last one, you guys should be able to do all these problems. The last problem I want to do is, let's see. Let's see, problem 89, I think, is the last one I want to do. 89, or was it 88? Or no, we just did 88. Or we did 86. Okay, we did that one in class. Oh my gosh, yeah. Oh, well, all these problems are the exact same. Okay, let's just do this. All right, so we'll do the reading time. No, I know I did that one for the video, and I know I did that one in class. Well, they're all the same. I'll just do the last one. So I'll just end with problem 91. So you're interested if men spend a different amount of time reading during the week than women. Suppose a random sample of 250 men and a random sample of 250 women are selected. Each person in the sample is asked to report the amount of time in hours he or she spends on reading. I've been doing this for too long. Let population 1 be men and let population 2 be women. The sample mean for men is 14.1. The sample mean for women is 13.8. Sample standard deviation for men is 0.6 and for women is 1.5. What is the null hypothesis? Well, we are trying to see if men spend a different amount of time reading during the week than women. So different amount of time means they are just not equal. So the null hypothesis says they're always equal, right? There is no change. There is no difference between mu1 and mu2. Well, the alternate hypothesis, we're looking for a difference. So these are my two hypotheses. So this guy should be correct. This guy should also be correct. Took them a little longer to figure that one out. Okay, so calculate the two-sample t-test statistic. So let's throw in all of our values here. So let's kill all this. We don't need this anymore. So first things first, I need my hypotheses. So my H sub O is mu1 minus mu2 is equal to 0. Then my alternate hypothesis. This is the stuff we did last time, so you should be okay with this stuff. And then not equals 0. Okay, so this is a two-tailed test. So after all the homework you guys are doing this weekend, you guys should be all right with this stuff. This is stuff we just finished. Okay, so what is the difference between our means? Mu1 minus mu2. It is 0. And why? Because we assume the null hypothesis is true. So we assume it's true. Then I need my x bar 1, x bar 2. I need my n1, my n2. And then I need my standard deviations, so my S1 and my S2. And then I will be done. I can find my test statistic. And now it's a difference between two means, so it's going to be t. And then I need my p-value as well. Okay, so my x bar 1, so that is the first mean it gave to us, right? Which is the men's mean, 14.1. So we have 14.1 for the men's mean and 13.8 for the women's mean. Okay, now I need my sample sizes. There were 250 each, I believe. 250 men, 250 women. That's in the second sentence. 250 men, 250 women. And then the standard deviations. So men is 0.6, so 0.6, and the women was 1.4. Right? Women, well, 1.5. Whoa, okay, 1.5. My test statistic then is the huge formula. So let's do this. So remember, it's the difference in my x bars. So my x bar 1 minus x bar 2 minus mu1 minus mu2, but mu1 minus mu2 is 0. So we don't have to worry about that. Then the square root of my S1. Now remember, S1 squared. Do not forget to square your S1. S1 squared divided by N1. Plus, when you're dealing with two means, your standard deviation is inside the square root, so you have to square it. So S1 squared divided by N1. Then it's S2 squared divided by N2. Okay, so that's my test statistic. So now my p-value, it's a two-tailed test. So I know my p-value is going to be a t.dist. It's going to be a t-distribution, but my test statistic is positive. So I have to look for, since it is a two-tailed test, I have to look for the, I have to find my p-value, which is the area in the direction of the tail that is closest. So since my test statistic is positive, the closer tail's to the right. So it's going to be 1 minus t.dist. Okay, your x value here. And then degrees of freedom, you just choose the smaller of your n minus 1. Well, they're both the smallest, so just choose 1. And then subtract 1 from it, and 1. Now this only finds the area, oh dang it, this only finds the area to, this only finds the area to, in one direction, but since it is a p-value, you have to multiply this guy by 2, right? So when you have a two-tailed test, the p-value for a two-tailed test, you have to multiply by 2. That's what I meant to say. So there we go. So that is my p-value. Okay, so well, first off, what do they want? They want my test statistic, so it should be this dude. Let's make sure it is correct. So throw him in there. It should be 5 places. Okay, took a really long time to figure that out. And then the p-value kind of scared me for a second there. Throw my p-value in here, and it's 5 places. So 1, 2, 3, 4, 5. Okay. And there we go. So then my p-value is less than 1%. So I'm going to reject it at any level. So I think alpha is usually 0.05. They don't tell me. But it's smaller than 0.05 and it's smaller than 0.01. So I'm going to reject the null hypothesis. And there you go. All right, so that's it. That's all the important problems from the non-credit final review. So you guys do the rest of them for extra help. But when I looked at the final exam, those are the ones that I figured would probably be most helpful. The problems that I did might or might not be on the final exam. You can choose whether or not you really want to focus on them or not. But I figured that was a pretty good overview. And that way also I'm not like, doing every single problem. So if I did every single problem, that would be like a 8-hour, 10-hour video. So check those problems out, do some of the problems on your own, and I hope that this helps. So good luck to you guys on your final.